Hello, everyone. Welcome to part 2 in our series on supervised sentiment analysis. This screencast is going to focus on some general practical tips for doing work in this space, especially focused on setting up a project and doing kind of pre-processing of your data. So first, I just wanted to give you links to a whole bunch of benchmark data sets in this space. We're going to concentrate on the SST and Dynascent, but there are a lot of other choices you could make, both for developing original systems and also supplementing training data that you've got for a particular application. Some of these data sets are really, really large, and they cover a diversity of domains. So these could be important assets for you. In a similar spirit, there are lots of sentiment lexicons out there. They cover different emotional dimensions and different aspects of the problem. And they too could be used to help you with powerful featureization. They could supplement features that you've created or help you group your vocabulary into interesting subcategories that would be powerful for making sentiment predictions. And these range from simple word lists up to highly structured multidimensional lexicons. Now, for a first pre-processing step, I thought we would just talk a little bit about tokenization, because I think that this can be a definitional choice that really affects downstream success. So just as a running example here, let's imagine we start with this raw text, which is a kind of imagined tweet. We have an @mention here. And then you can see that some of the markup has gotten a little bit garbled. We have an emoticon that looks sort of obscured and a link at the end. I think as a very preliminary step, even before we tokenize, we might want to isolate some of that markup and replace the HTML entities. It's a pretty easy thing that you can do that could really make a difference. Now we've got our apostrophe, we've got our emoticon intact, and then we still have the link and other things in here. So even before you do that, you might check to see whether a simple replacement of the HTML entities would make a difference in your data. Now we begin the tokenization question, and I think a good baseline choice here would be simply Whitespace tokenizing. We're going to split on Whitespace and treat all the resulting strings as tokens. So that would take our raw text up here and split it up as you can see on these independent lines. This looks okay to me. So we're going to have a problem with our @mention because it has this colon on the end. So we might miss the fact that this is the actual @mention. The unigrams look okay, although the date has been split apart. We've preserved our hashtag. We've got this token that might appear only once, even though there's a clear, consistent signal there. We do have our emoticon, and our link is mostly intact, although this period could be disruptive if we actually want to follow the link, because it's still glommed onto the end of the URL. Treebank tokenizing is another very common scheme in NLP, I would say at this point, largely for historical reasons. The way Treebank tokenizing works is it takes this raw text and splits it up into a whole lot of tokens, right? In comparison with Whitespace, we have a lot of distinct pieces here, and this really looks kind of problematic, right? So we have destroyed our @mention. We don't have that username anymore. It does this interesting thing with words like can't, that they get split apart into 2 tokens. We've lost our date. We have lost our hashtag. This is possibly good. So yay has been split up according to its punctuation. So we have now 4 exclamation marks separated out from this word here. But our emoticon is completely lost and our link has been really destroyed. So this looks problematic from the point of view of accurate featureization and also doing things with social media. So that kind of brings me to what we might want from what I've called a sentiment-aware tokenizer. We would like it to isolate emoticons clearly because they can be really sentiment-laden. We want to probably respect Twitter and other domain-specific markup because that's often the space in which our data come from and the kind of place we want to make predictions in. In a similar spirit, you might take advantage of underlying markup. Maybe don't filter off the HTML because there could be an important signal there. You might be aware that the website or data producer might have done some pre-processing of their own that might disrupt things like curses, which could, of course, carry a lot of important sentiment information. You might want to preserve capitalization because, of course, that could be used for emphasis. In a similar spirit, you might want to regularize emotive lengthening like yay down to just 3 characters here to capture that it is an emotive lengthening, but also regularize all those distinct tokens. And then as a stretch goal, although this might be less important in the era of contextual models, you might think about capturing multi-word expressions that carry sentiment. Just think of an example like out of this world, which is positive, but none of its component pieces are positive. So many models will miss that that is conveying clear sentiment. Whereas with a clever tokenization scheme, you might capture that as one single token. So here's a simple example that meets a lot of those goals here for a sentiment-aware tokenizer. We begin from our usual raw text. We normalize and preserve the @mention. We keep most of these words intact, and we kind of capture that that June 9 thing was a date. Preserve the hashtag, of course. We're treating all of these potentially emotion-laden punctuation marks as separate unigrams. I think that could be good. Of course, capture the emoticon and capture the link. Right? And if you want something that meets more or less all these criteria, except I think the date normalization, you could just use the NLTK tweet tokenizer. It's a good, simple choice that you could make that I think will be useful for sentiment analysis. And to quantify that a little bit, here's some experimental evidence that I think is going to be relevant to the kind of work that you all are doing. So my data is open table, that's restaurant reviews, short ones. I've got 6,000 reviews in my test set. And what I'm doing along the x-axis here is varying the amount of training data that these systems can see. It's simply a softmax classifier, and my primary manipulation is I have the sentiment-aware tokenizer in orange, Treebank in green, and Whitespace in gray. And the picture is pretty clear, right? Along the x-axis, we have accuracy. It's a balanced problem. And what you can see is that the sentiment-aware tokenizer is the clear winner here, especially where training data are sparse. In the limit of adding lots of training data, I think we can make up for a lot of shortcomings of tokenizers because we see a lot of redundancy in the training data. But where data are sparse, the sentiment-aware tokenizer is clearly a good choice. And another thing I would add is that because it produces more intuitive tokens, the sentiment-aware models might be more interpretable in some sense. And to really connect with the homework that you all are doing and the bake-off, this is what happens when we go across domains. So here I'm training on open table restaurant reviews, but I'm going to test on movie review sentences here. Otherwise, this is the same experimental paradigm. Because of the cross-domain thing, the results are a little bit more chaotic. But I think, again, the sentiment-aware tokenizer is a clear winner with the largest gains where training data are a little bit sparse. And that's the expected picture. So be thoughtful about tokenizing. As a counterpoint to that, I've called this section on stemming the dangers of stemming, because what I want to try to do is convince you not to stem your data. But first, what is stemming? So stemming is a kind of pre-processing technique that would collapse distinct word forms. There are three common algorithms for this, easy to use: the Porter stemmer, the Lancaster stemmer, and the WordNet stemmer. And my criticisms are largely leveled at Porter and Lancaster. Here is the bottom line. In doing this kind of stemming, you are apt to destroy many important sentiment distinctions, making this a counterproductive pre-processing step. On the other hand, the WordNet stemmer does not have this problem. It's much more conservative, but it also doesn't really do enough to make it worthwhile. It's kind of costly to run and has some requirements that might make it simply not worth it. And I would say that the bottom line here for stemming is that in an era where we have very large sentiment data sets, the function of stemming would be to collapse the size of your vocabulary and make learning more easier in small domains, but we mostly don't confront that problem anymore. But just to drive home this point here are some examples focused on the Porter stemmer of cases where running the Porter stemmer actually collapses clear sentiment distinctions according to the Harvard Inquirer, which is one of those lexicons I mentioned before. I've got defense and defensive. They get collapsed down into this funny non-word defends. Extravagance and extravagant, different sentiment, collapsed down into this word fragment, and so forth for these other examples. And I think this is showing that in pre-processing your data, you might be removing some important sentiment signals. The Lancaster stemmer uses a very similar strategy and has arguably even more problems in this space. Here we've got the positive word complement and complicate. According to the Harvard Inquirer, again, they could both get collapsed down into what is a completely distinct word, comply, and that should be concerning for many reasons. And the other examples make a very similar point. The WordNet stemmer I mentioned before, I think this actually has something going for it. And there might be cases where you'd want to use it. It's high precision. It requires word part-of-speech pairs. And the general issue is just that it removes some comparative morphology. That's the only thing you might worry about for sentiment. But otherwise, it's going to take like exclaims, exclaimed, and exclaiming and collapse them down. That could be a useful compression of your feature space. It will leave exclamation alone, which I think is good. Similarly for these things, they all kind of get preserved across the two verb forms, but we preserve the adjective as different. I think that could be good. And as I said, the only concern would be that happy, happier, and happiest all go down into their base form, whereas I think these could encode different gradations of sentiment that you might want to preserve. So that's worth some thought, but overall, I think you probably want to avoid doing stemming. And to bring that home, let's return to my experimental paradigm. Using a softmax classifier, open table reviews, 6,000 of them in my test set. And here along the x-axis, I'm varying the amount of training data I have. And I think what you see is that the Porter and Lancaster stemmer in purple and black respectively are kind of forever behind, right? Versus just simply sentiment-aware tokenizing. It gives you a lead. The lead is especially clear as you get out of this very sparse domain here with very few training instances. To close, just a few other pre-processing techniques that you might think about. So you could part-of-speech tag your data in the spirit of trying to capture more sentiment distinctions that you might capture otherwise. So just for example, arrest or like arresting as an adjective is positive, but arrest as a verb is typically negative. Fine as an adjective is positive, but to incur a fine as a noun is negative, and so forth. You can see that some sentiment distinctions actually do turn on the part-of-speech of the word. So treating all of your unigram features as based in word part-of-speech tag pairs could be useful for preserving some of these distinctions, again, as a pre-processing step to help your model be more attuned to these points of variation and comparison. But there are limits even to this, right? So this is just some cases on these slides where even within the same part of speech, we have an adjective that in one sense is positive and another negative. For example, the adjective mean can mean hateful, but it can also mean excellent, as in they make a mean apple pie. Smart as an adjective could be both painful and also bright and brilliant and so forth like that. And similarly for serious and fantastic and sneer, depending on the context and the intention of the speaker, they can kind of cut in different directions. So even part of speech tagging is going to be limiting when it comes to really recovering the underlying word sense, even for something as low dimensional as a sentiment distinction. Finally, now this is another powerful technique that you might use and think about as you select and evaluate different models. This is what I've called simple negation marking. And the phenomenon is just that if I have a verb like enjoy, which sounds positive in isolation, of course, its contribution to the overall sentiment will change depending on whether it's in the scope of a negation. I didn't enjoy it is negative. And negation can be expressed in many ways as this modifier of auxiliaries like not, but as an adverb like never. It could be in the subject like no one, and it could even be really inchoate for things like I have yet to enjoy it, which is a kind of negation. And then of course the negation in 5 here is very far. I don't think I will enjoy it is probably negative, but the negation is way far away from the verb that we want to have it, that we want to, whose sentiment we want to modulate with the negation. So here's a very simple method that I think was first explored by Dawson Chen. It's also used in Pang et al. These are classic early sentiment analysis papers. And the idea is simply to append a neg suffix to every word in the sequence that appears between the negation and some clause level mark of punctuation to sort of roughly indicate the semantic scope of the negation. This is a simple pre-processing step, highly heuristic. It would take a sentence like no one enjoys it and literally turn the unigrams one enjoys and it into variant forms of them where one has a neg appended to it, and so does enjoys and so does it. And the idea is that in doing this, we're giving our model the opportunity to discover that enjoys in this context is actually a different token in some sense than enjoys when it's not in the scope of negation. And for many of the linear models with hand-built features that we explore, simply making that initial distinction might create some space for your model to learn the interaction of negation with these other features. And just to quantify it a little bit by way of rounding this out, I think this slide shows the impact that this can have despite its simplicity. So similar, we have open table as our test set. We're using a softmax classifier, and the x-axis is again varying the amount of training data that we have. The Whitespace tokenizer is in gray, it's the worst, followed by Treebank in green. Then we have that sentiment-aware tokenizer in orange. And then way above them, consistently for all parts of the data here, are sentiment-aware plus that negation marking. That is obviously the superior model for all kinds of amounts of training data. And I think what that's showing is that the influence of negation is actually really real and severe in a lot of sentiment data sets. It's just very common to combine sentiment words, positive or negative, with negation, and it has this predictable effect of kind of flipping the value. So in doing this sentiment and doing this negation marking, we're giving our model a better chance at discovering exactly those distinctions. And here's a similar set of results for cross-domain, where I'm starting on OpenTable and testing on IMDb. Again, the results are a little bit more chaotic, but I think it's a clear win for the sentiment-aware plus negation marking model.